In this optimization problem, I want you to imagine a wire, like the one that I've written down here, and I kind of color-coded it a little bit. The question is, how can I take this wire and fold it up into a rectangle, fold it up into something that looks like this? So the same wire, but it's being moved around into either a square or a rectangle. Now, if I do that, and I can do it in different ways, so for example, this one looked like a square, but I can take the same idea, but make the blues a little longer and the yellows a little shorter, and it makes more of a clear rectangle when you fold it. The question is, of all of the different ways where I could fold it and make a rectangle, which of them gives me the largest area? Which of them inscribes the largest area? Now, this is an optimization problem. In effect, we're going to make a derivative and set it equal to 0, and we're going to try to solve it that way. But the hardest part about this example is trying to do all the setup, trying to figure out how do I write down the equations in what ways and where do I put variables down. So that is the key to many different optimization problems. It's the interpretation. So if I'm thinking about this particular wire and I'm trying to figure out where to fold it, one of the things that I note is that there's a top and a bottom. They are the same length. And there's two sides. They're the same length. So if the entire wire has a length L, I can break it up in the following way. So I've got this entire wire with its length L, and I say that the two blue portions, so this is the bottom and the top, they're the same length. I'll call those X. And then the two yellow portions, the Y's, those are the sides of my little rectangle when I fold it up, that's going to be called Y. So I want to try to figure out, what is the constraining equation, what is restricted here, and what is the optimizing equation? The constraint that I have is the following. The total length of this wire is L, and when I look at it this way, I can see that I've got two X portions and two L portions. So this gives me the constraint that twice the value of X, because there's two of them, and twice the value of Y, that has to equal to L. So that's my constraint. That is what is restricted here. So that's my first equation. My second equation is the so-called optimizing equation. The thing I care about is the area. So this is what I'm actually interested in. I want to maximize the area. And this is just going to be, it's a rectangle, just the X times the Y, the base times height. This is my optimizing equation. Now, the problem with just taking the derivative of the optimizing equation, going right away and just taking the derivative, is that there's two different variables. There's an X, there's a Y. It's not a function of one variable where you can use the techniques of single variable calculus. But what I can do is I can take this constraining equation and I can try to manipulate it and I can try to get it down here in the optimizing equation. I want to get rid of one of the variables. I don't know if you have a preference. How about this? I am going to solve the top one for Y, and I'm going to put the Y down into here, which will mean I will now only have X's remaining. So I'm going to get rid of the Y by solving the top for Y and plugging it in. So how can we do this? I think we can do this one in our heads. So the first X that's right there, that just comes out. Now I'm going to replace my Y. So in this long equation, I've got the 2Y equals L. Let me subtract off the 2X, so L minus 2X. Divided by the 2, that leaves me with a Y. So what do I have? It's going to be L minus 2X, and then all divided out by 2. All right. So there is an area formula that is now only in terms of X. And if I wanted to distribute it through just to make my next derivative a little bit easier, I can say this is L divided by 2 times X. So that's talking about the first term. And the second term is going to be minus X squared, where that 2 and that 2 cancels. Pretty good. Now I think I can compute the derivative. So let's go along and do the derivative of area with respect to the value of X. I can actually compute this thing now. What's it going to be? Well, L over 2 times X, its derivative is just going to be L over 2. Minus X squared is going to go to minus 2X, and I want to set this equal to 0. Pretty easy to rearrange. I can go and say that X is going to be moved over to the other side. X is equal to L divided out by 4. So I have a value. Given any length, what's the X supposed to be? The X is supposed to be L divided out by 4. Now, whenever I have this critical number, that's all I've computed, is a critical number. I'm conjecturing it's going to be the maximum, but I don't know that for sure because I haven't tested the endpoints, and I haven't done any first derivative test to see whether this really is going to give me the maximum. So let's do the endpoints first. Well, one endpoint, if I think about this, would be maybe x was equal to 0. Okay, if I plugged in x equal to 0, the area would be 0. The other possibility would be that x was equal to exactly L divided by 2. So this would be the rectangle, if you really want to call it that goes straight up, has no height, and goes straight back. So in other words, the y would be 0 if the x was L over 2, because twice x would be the entire thing, the L. So the one endpoint was 0, the other one is L over 2, but that gives a y of 0, and the area at 0 would again be 0. So the endpoints are clearly not maximums. And then, because there is clearly non-zero possibilities here, this means that this single critical point has to be the positive, has to be the maximum. If you prefer, you could also talk about the first derivative test. If I look at this particular equation here and see that if I increase my value of x, it's negative. If I decrease the value of x, it's going to be positive. So it's going to have one of these things where it's going increasing to decreasing. It's going to be a maximum by the first derivative test. Either way, this is going to be the maximum. The final thing I want to think about is what happens geometrically. Like, what does this solution sort of look like? Well, if I think that x is L over 4, and I've got two different places where there's an x, so that takes up L over 2. It takes up half of the wire. So then the y's take up the other half of the wire. That forces that the y is also equal to L over 4. I've got 4 of these different line segments, and each of them are L over 4. So it's L over 4, L over 4, L over 4, L over 4. It is a square.